Hi students, in the previous lesson we looked at the product rule for square roots and we used it to simplify square roots, but today we're going to use it in a different way. We're going to use it to multiply square roots. So let's remember the product rule. It said that if we have the square root of a product, we can write it as the product of the square roots. And it works in either direction. And today we're going to take the product of square roots and we're going to write them as the square root of a product. So let's look at some examples of multiplication. We've got the square root of 3 times the square root of 5. Now neither of those are perfect squares, so we can't evaluate either of them unless we use a calculator to get an approximation, and we don't want any approximate answers. We want exact answers. So what we can do though is we can rewrite this as the square root of the product, and then we can actually multiply under that square root. 3 times 5 is 15. And this is our answer, and it might not seem like this is any better than what we started with, but what we started with, we had 2 radicals, and now we've combined them into 1. In general, we don't want more than 1 radical. If we're able to combine them, we should. And then also, of course, we want the smallest number inside the radical. Let's look at another example, and in this one it's going to be even more helpful to use the product rule. Let's look at the square root of 2 times the square root of 8. Now these are not perfect squares, so we can't just evaluate either of them. But we can use the product rule to multiply them under 1 radical. 2 times 8 is 16. So we can write this as the square root of 16. And that is a perfect square, so we can evaluate it, and we get 4. Now, which is simpler to understand? The square root of 2 times the square root of 8, or 4? Definitely 4. So by combining these radicals into 1, we put ourselves in a position where we might be able to evaluate it and get rid of the radical. But even if we can't, we can express it with only 1 radical, which is simpler than 2. Let's do a couple more. Let's look at the square root of 3x times the square root of 6x. Again, these aren't perfect squares, so we can't evaluate them individually, but we can use the product rule to multiply them. 3x times 6x is 18x squared. And this, again, isn't a perfect square, but it does contain perfect square factors. We can factor this out. 18 is 9 times 2. And then x squared is a perfect square, so we put it out front there. And then we can evaluate the square root here. The square root of 9x squared is 3x. So we end up with 3x root 2. Now there is a small caveat here. When I took the square root of 9x squared and got 3x, there's something we have to be careful with. And I'm actually going to talk about this in another video because it is a concept that we need to talk about, but I don't want to talk about it with the rest of things because it's kind of a technicality. So I will put that in a separate video. For now, we're just going to continue on to one more example, and then we're going to look at adding and subtracting square roots. So let's do one more. This time we're going to look at the square root of 1/2 times the square root of 9/32. Now, 1/2 and 9/32 are not perfect squares, so we can't just evaluate either of them, but we can use the product rule to multiply these. We multiply fractions straight across, so 1 times 9 is 9, 2 times 32 is 64. And this is a perfect square. The square root of 9/64 is 3/8. Because 3/8 times 3/8 is 9/64. So in this case, we were able to evaluate that square root. Next, I want to talk about adding and subtracting square roots. We've looked at multiplying, and we're going to continue looking at multiplying a little bit later, but right now I want to look at adding and subtracting square roots. Now, adding and subtracting square roots is kind of like combining like terms. If we had 4x plus 3x, we knew we could add those together to get 7x because we had like terms. The variable parts were the same. And it works similarly when we're dealing with radicals. If we have 4 root 5 plus 3 root 5, because each of these has the same radical part, we can combine them by adding the numbers out front, and we end up with 7 root 5. Just like the variables stayed the same in the beginning, the radicals are going to stay the same here. So if we have 4 root 5s and 3 root 5s, we end up with 7 root 5s in the end. We can combine these because they are like radicals. Let's look at a few more like radicals that we can combine. Let's look at 8 root 13 plus 9 root 13. Are these like radicals? They are, because each one has the same radical. So we can combine them by adding the numbers out front. 8 plus 9 is 17. So we get 17 root 13. Let's take a look at a couple more. Let's look at the square root of 17x minus 10 times the square root of 17x. Are these like radicals? Yes, they are. They contain the same radical parts, so we can combine them. There's no number out front of the first one, but we can think of there being an invisible 1, and so 1 root 17x minus 10 root 17x gives us negative 9 root 17x. All right, we're going to look at 2 more, and then we're going to move on to some problems that involve multiple steps. Let's take a look at the square root of 3 plus the square root of 5. Are those like radicals? Unfortunately, they're not, because 3 and 5 are different numbers, so we can't combine them. So all we can do is write root 3 plus root 5. That's one that can't be simplified. And one more, the square root of 8 minus the square root of 2. Now, these aren't like radicals as they're written. However, there is something we can do here. Do you see it? 8 contains a perfect square factor, so we can simplify the square root of 8. We can split it up into 4 and 2. So I've just rewritten the square root of 8 as the square root of 4 times the square root of 2. Now we can evaluate the square root of 4. That's 2. So we've got 2 root 2 minus root 2. And now they are like radicals because each one has a root 2. We can write in the imaginary 1 out there, and then 2 root 2 minus 1 root 2 is 1 root 2, or just root 2. In the next video, we're going to look at some problems that involve more than one step with multiplying and adding or subtracting.